Thanks. So, although I had given a title of capsules and vesicles under electric field, I will predominantly be talking about elastic capsules in this talk. Okay. The work was done by Rahul, Sudeep, Shivraj. The three have graduated, and Joy does experiments on vesicles. I will show few experiments on vesicles. So, the outline of my talk is there are 4 parts to my talk, and this kind of an overview of my work in elastic capsules over the last 5 years. I will first talk about a method to characterize what I call as water in oil capsules, okay, and then talk about 3 different scenarios of water in water capsules, capsules in DC fields, in AC fields, and if time permits, I will talk about biconcave discocytic capsules which resemble red blood cells under electric fields and elongational flows. So, the tools I typically use are analytical theory using spherical harmonics, low capillary number asymptotic expansion. I do boundary element simulations and a few experiments. So, the theme of my group normally is to look at spherical objects, deformable objects under electric field, which I classify as drops, capsules, vesicles, and cells, and they differ in predominantly in a way they resist deformations, resist normal deformation. For example, a drop has an intrinsic interfacial tension. On the other hand, capsules and vesicles do not have tension in their rest configuration, and they generate tension as a response to applied deformations. Okay. A cell, for example, a red blood cell would be a combination of capsules and a vesicle. Okay. So, the difference between capsule and vesicle essentially is the constituents which go on to form the wall. The vesicle is typically made up of lipid bilayer membranes and is characterized by zero shear elasticity. Okay. So, if you have deformation, a vesicle cannot resist shear deformation. A capsule, on the other hand, can resist shear deformation, and this leads to very different response to normal deformation. For example, in vesicles, the tension will always be isotropic. It could be compressive or tensile, but it's always isotropic. Whereas in a capsule, you can have anisotropic tensions, which could be compressive or tensile. The other difference between a capsule and a vesicle is because a vesicle is area conserving. If you start with a sphere, a vesicle cannot deform. A capsule, on the other hand, can have a spherical reference state, a rest state, and it can deform even if it's a spherical geometry. Okay. So, the idea here is to look at microcapsules which are of the sizes of around all the way from hundreds of nanometers to tens and hundreds of microns, and they are promising agents for, say, drug delivery or encapsulation of different agents. So, it essentially consists of a droplet of a fluid which is covered by a shell which we would call as the capsule material, and then the idea is to the idea of having encapsulation is to have the encapsulated material for a longer period of time in an application, and then have a controlled release whenever it is so required. Okay. Now, because I will be using electric field, it's important for me to distinguish between the medium phase especially, and so I have classified the capsules as water in oil capsules. What I mean by water in oil capsules is the interior core is an aqueous drop and the outer phase is an oil phase, and these could have applications, for example, in agricultural sprays where you often have an organic medium. It could also be in textiles, capsules used in textiles where you can have an organic material which is in the medium or in the aqueous phase. Okay. So, these are different from what I would call as water in water capsules, and the simplest example of a water in water capsule will be a red blood cell where you have the inner core which is aqueous and which is suspended in a medium which is also aqueous. Okay. I'll talk about spherical water in water capsules, but one of the most popular example is a red blood cell, as you know, which has a biconcave discoid shape, and I'll talk about electrohydrodynamics of a biconcave discoid shape as well. It's not just about the naturally occurring red blood cells. There is a big promise of having capsules which are biconcave discocytic in shape. For example, these synthetic capsules made in the Mitragotri group, and they are known to have advantages in drug delivery because of their resemblance to red blood cells. Okay, so this will be forming the second, third, and fourth part of my talk. Okay. Now, when you look at the capsules, you are worried about their surface elasticity, and typically the deformations are large, so one would worry about finite deformation. And so if you have a reference surface with tangent vectors A1 and A2, which goes into a deformed state like this, one can always, and these are embedded in a continuum of zeta 1, zeta 2, zeta 3, you can always have a mapping of the deformed configuration to the reference configuration through the embedded space. So one can write a three-dimensional deformation tensor and convert it into a Cauchy-Green strain tensor. And if you want to project it onto the surface, you could have the projection operator pre and post multiplying the deformation tensor. Okay. A more common way in this literature is to write the deformation in terms of change in the length of this element on the surface, and one can identify the Green strain tensor, which is Lagrangian, or the Almansi strain tensor, and these are kind of finite deformation measures of deformation. And the eigenvalues, for example, of the Green strain tensor are given by half lambda I squared minus 1. These are the eigenvalues, and these are two principal eigenvalues with two principal what are called as the stretch ratios lambda i's. Okay. I will give an example which will make it clear. If you consider biaxial extension, for example, of a strip with coordinates A1 and A2 and deform it into an elongation x1 and x2, then one can easily write the components of the strain tensor. Now, one can relate these finite deformation strain tensors to small strains, okay, in this manner. And one can, for example, easily derive a finite deformation Hooke's law or the generalized Hooke's law starting from a small strain Hooke's law. Okay. And you simply replace the small strains with the finite strains and finally represent it in terms of the stretch ratios, you get the finite deformation Hooke's law. But what is more popular in literature in capsules are these two laws, the Skylark law, which is known to describe the red blood cell membrane fairly faithfully, and the Muni-Rivlin laws. The Skylark law is known to be strain hardening, whereas the Muni-Rivlin laws are strain softening. The Neo-Hookean, for example, turns out to be a special case of the Muni-Rivlin law. And what you have here essentially is the principal tensions are related to the principal stretch ratios through moduli, and G, for example, is the shear modulus, which is related to the Young's modulus through these expressions. In the red blood cells, where you use the Skylark law, it's important to know this parameter C, which is a penalty to the area change. And the higher the value of C, you have more and more incompressibility of the membrane. Okay. So with this background, the first part I've tried to motivate in our group. For example, in the last couple of years, we've tried to develop this method of characterizing the membrane properties using electric fields. And there are several methods available in the literature to determine the surface elasticity, for example. But the methods which are gaining popularity are, for example, looking at the deformation of a microcapsule through a capillary, and then coming up with analytical or numerical calculations to describe these shapes and then back out the elasticity. In the same way, for example, you could have a spinning drop rheometer where you spin a capsule, measure the deformation, provide an analytical theory for deformation versus the spinning speed, and then back out the elasticity. Okay. So towards this, we thought of applying electric fields and trying to estimate the surface properties. So we do small deformation theory in this problem, and we do axisymmetric calculations where the principal stretch ratios are now the meridional stretch and the azimuthal stretch, and the definitions are clear. The meridional stretch is simply the change in the arc length from the reference configuration, whereas the azimuthal stretch ratio is the change in the circumference at any particular r. Okay. Now this you can write the generalized Hooke's law, And the generalized Hooke's law is reduced to the small strain Hooke's law in the limit of small deformation. So we do small deformation analysis. The idea here is to start with a spherical configuration, deform it into spherical harmonics, the shape into spherical harmonics, get the deformations, so get the displacements ur and u theta, and then relate ur and u theta to the small strains, so that you have the small strain measures. Then use the Hooke's law to get the elastic stress and equate it to the electric stress, okay, and do what I call as the elastostatics force balance. So you essentially have an electric field, you deform the capsule and equate the elastic stress to the electric stress, and you get a measure, you get an expression for the deformation, okay. So the idea here is to write the Maxwell stress tensor. Let me just introduce the Maxwell stress tensor. If you write the force per unit volume for a parcel of fluid with free charges rho subjected to electric field E, then there is this force on the free charge. Then you also have dipoles in the system which experience a force because of a gradient in electric field, and then you have a term which is because of the interaction between dipoles. So the net force per unit volume, the electric force per unit volume, can be conveniently expressed as a divergence of a tensor which is called as the Maxwell stress tensor, okay. So if you do this analysis, so let me just go through further. So as I said, I am looking at water in oil capsules, and in in this literature, water would typically be considered as a perfect conductor. The conductivity of water would be 10 power 6, 10 power 7 times higher than that of the oils, and so you can assume it to be a perfect conductor. There are no electric fields present inside the water droplet. And so the electric field is present only in the oil medium, and so you can write the Maxwell stress as squared of the electric field in the outer medium. Okay, so with this, if you solve it in the spherical harmonics, you can get the force on the surface of an elastic capsule, which comes out to be this, and from this you can get the degree of deformation. Okay, so I define the degree of deformation, the Taylor deformation parameter, as the change in the major axis divided by the minor axis, okay, such that the degree of deformation is 0 for a spherical object, okay. And the analysis then gives us this compact expression that the degree of deformation is 9 by 16 times the capillary number into 5 plus the surface Poisson ratio. So remember, the surface Poisson ratio is 1 for an incompressible medium, unlike half for a 3D medium. And so the idea is to apply electric fields, measure the deformation. Once you know the deformation, you can calculate the elasticity of the capsule. Okay, so this gives a very easy way to determine the elasticity of the capsule. Now, if you want to do finite deformation studies, we do the boundary integral method in the Stokes limit. This is the Maxwell stress, and then this is the elastic force at the interface. So as I argued in the beginning, the elastic force will be related to will be given by the specific constitutive laws, the finite deformation constitutive laws. And there are two components to the elastic force. The normal component, which is dependent on the meridional curvature multiplying the meridional tension, and then the azimuthal curvature multiplying the azimuthal tension. Okay, and then you have a Marangoni kind of stress because the tension can vary along the arc length. Okay, so with this you set up the boundary integral equation. You solve for the electric field using the integral equation for the potential, so that you can get the tangential fields. In this case, the tangential fields are 0, and then you solve for the velocity fields. You start with an initial configuration of a capsule, divide it into nodes, move the nodes, get the new configuration, and so on. So if you do that and plot the deformation versus capillary number, you get a fairly good agreement between the analytical theory and the boundary integral calculations, and then you see some small deviations in this. Okay. Now, one would have been puzzled if I use Hooke's law, for example. The expression for degree of deformation is 9 by 16 capillary number 5 plus nu s, and one would argue that if the Poisson ratio is 1, one shouldn't have seen any deformation in a spherical capsule, right? But the expression kind of tells you that the degree of deformation is very weakly dependent on the Poisson ratio, which means that even if the Poisson ratio is 1, you can have significant deformation in the capsule. Okay. And this really is an artifact of the fact of the linear assumption. And so to confirm that there is some issue with this, we actually compare our results with the boundary element calculations. And you find that if this is the linear theory prediction, as you increase the Poisson ratio to a value of 1, so I go like this, you see that the degree of deformation indeed decreases as is expected. So there is strong deviation from the linear theory as the Poisson ratio approaches 1. Okay. So this is one aspect I wanted to show about the boundary element calculations. Now if you plot the value of the azimuthal stretch ratio and the meridional stretch ratio, it's actually the change in the area of the capsule. And if you plot it as a function of arc length, you see a reduction in the area around the equator. This is the equator, these are the poles. And if you plot the corresponding stresses, you get these plots. Okay. So let me first show you the Maxwell stress distribution. If you see the Maxwell stress distribution, you see that because your droplet phase is a perfect conductor which is embedded in a perfect insulator, in this case you get the Maxwell stress to be maximum at the poles and kind of compressive at the poles. They are tensile. You see the Maxwell stresses are tensile, and then they are compressive at the equator. And this is reflected in the tension built in the capsule. So you see that whereas the meridional tension is always tensile, the azimuthal tension is compressive at the equator. Okay. And so this is something to be remembered, that the azimuthal tension is compressive at the equator, and we'll see this we'll have some implication. So we did some experiments with a standard capsule. The monomer here is octadecyl trichlorosilane. It has an 18 carbon chain with a silicon and 3 chlorides. So it's kind of a surfactant. And so the experiment consisted of taking oil, silicone oil, which is an insulating oil, and you have OTS dissolved in it, and then you simply put a droplet of water, and it's pictorially shown here. This is the droplet of water. You have the OTS surfactant molecules which migrate to the interface because of their surface activity, and then these reactions take place. Okay. So you have the trichlorosilanes getting hydrolyzed to silanols, and then these silanols can undergo condensation to form a crosslink. Okay. And so essentially you have these crosslink networks which form a interfacial skin at the oil water interface. Okay. And that's what we would call as a capsule. It's a water in oil capsule. Okay. And so now you can estimate elasticity and maybe compare it with some other methods in the literature. And so here are plots. This reaction is known to be sensitive to pH. The hydrolysis step, for example, is different at low pH and high pH for very chemistry specific issues which I won't get into. So we did these experiments of you just take the capsule, apply electric field, measure the deformation, and then back out the value of elasticity from these plots. Okay. The typical experiment would look like this. You put a electric field, it deforms, it remains at a equilibrium deformation, and then you switch off the field, it relaxes back. So these are kind of, and we kind of guarantee that the capsule is elastic only if it comes back to its reference state of a sphere and it doesn't have a residual elasticity, okay, residual deformation. So if the capsule has a residual deformation, we call it as plastic deformation. Okay. And from this we could estimate the Young's modulus, and the values of the Young's modulus we got of around 0.5 to 0.6 Newton per meter, which is in agreement with the values in the literature. Okay. Now, so you could take these capsules and apply stronger and stronger electric fields, and we find that at certain critical electric fields, you start seeing wrinkles in the capsule. Just a second. And we then use the theory of, so you would see these wrinkles. One can then estimate the wavelength of these wrinkles, and the wavelengths of these wrinkles change with the applied electric field. Okay. So if you use the value of Sereda and Mahadevan, and so these wrinkles are essentially forming because there is a tensile force, electric force, as I showed, which act on these capsules to pull it away, and then there is a compressive stress at the equator, and then the two together are really responsible for these wrinkles. So if you use the value of, if you use the expression by Sarada and Mahadevan, you find that the bending modulus is given by this tension into lambda raised to 4. And since we know the electric tension in the system, the wavelength should really scale as e raised to minus half. Okay. And if the wavelength had scaled as e raised to minus half, you would get a bending modulus which is independent of the electric field. What we find in these experiments is a wavelength dependence which is roughly around 0.4, and with this we actually can find the bending modulus, and once you find the bending modulus you can also find the thickness of the membrane, okay, and we get the thickness of a membrane as the function of pH. Okay. So essentially the method then allows you to completely characterize an elastic capsule by estimating its by knowing its Young's modulus, its bending modulus, and the thickness of the membrane. Okay. Now, so we kind of improvise this method to understand the kinetics, okay, and the experiment here consisted of measuring deformation of a capsule as a function of time, and you keep the field on for a very short time, measure the deformation, and then switch it off, and then at regular intervals you do this experiment. And what we find is that if you are in the low pH regime, you see that there is this phase where the degree of deformation initially increases, and I can explain it later why it should increase. It's essentially because of the surface activity of OTS. So you have a phase where the deformation doesn't change much and then it starts decreasing, and we conjecture that this is the hydrolysis phase and this is the condensation phase, and at low pH you indeed see a very slow hydrolysis phase and a rapid condensation phase, whereas if you go to high pH, as I said, the hydrolysis is pH sensitive. At high pH we don't see any hydrolysis step, and there is a very fast condensation step. Okay. So this kind of allowed us to estimate kinetics of hydrolysis and condensation kinetics as a function of pH of the solution. It's kind of a very easy method. This kind of the recipe we now follow. We first get the kinetics of any new system which we look at, get the hydrolysis and the kinetics of the condensation steps and so on. But what we could do is take advantage of the fact that the hydrolysis step is slow and actually made anisotropic or non-spherical spheroidal capsules by simply conducting the synthesis in the presence of electric field. So if you if you put a droplet of water in oil with OTS and apply electric field, the capsule deforms because the hydrolysis step is slow, it deforms, and then simultaneously condensation takes place, and at the end of around 20 minutes you switch off the field, the capsule gets arrested in the non-spherical shape, and we could get several capsules of anisotropic shapes. Okay. Now my dream at least has been to use this system as a rheometer for doing surface rheometry. And there are issues with surface rheometries. If you do surface rheometry with spinning drop tensiometer or pendant drop tensiometer, you can hardly go beyond a frequency of around 1 Hz. Okay. Whereas in the electrohydrodynamic method, one has actually an access to several range of frequencies, and one can then estimate the loss and storage moduli as a function of frequencies all the way up to hundreds of hertz. And there are applications at least in refining, in petroleum refining, where interfacial rheometry is required at very high frequencies, but there are no instruments as of now to do that. Okay. So this is still a dream. What I could do in the meantime is get expressions for a capsule in an AC field. This is for a water in oil capsule, and the advantage of a water in oil capsule subjected to AC fields is that all the electrostatic timescales are so fast that the dynamics is only determined by the interfacial dynamics. Okay. So the membrane viscosity and the membrane elasticity determines the dynamics, and one can get expressions for the deformation. Okay. So if you apply AC fields, you get a deformation which is also oscillatory, and the deformation has a steady part and an oscillatory part, and we could derive expressions for the steady and oscillatory part. I won't get into details of this, but one can get expression for the phase lag between the applied voltage and the deformation, and this phase lag is really related to the membrane viscosity. Okay. So what is called as the Buznik number in literature, which is the ratio of membrane viscosity to the fluid viscosity. Okay. So if one simply measures the phase lag and the degree of deformation, one can in principle completely characterize the capsule for its viscosity and elasticity as a function of frequency. We also have expressions now for a viscoelastic membrane which is subjected to startup or relaxation. And then if one estimates, if one experimentally gets these curves, one can fit in these expressions and get the membrane viscosities and elasticity. Okay. So this is what I have to say about the water in oil capsules. I'll now move on to water capsules. And the best example, as I said, for water in water capsules are the red blood cells. They are more common with vesicles, which are basically bilayer membranes. And the application of electric field in these capsules or vesicles, there are at least 3 main applications I can think of which is driving the research in this area. The first is electroporation, which is basically punching holes in lipid bilayer membranes using strong electric pulses, and then using it for electrochemotherapy or electrofusion. The other is dielectrophoresis, where you use different electric fields to migrate cells or vesicles to regions of strong or weak electric fields. And then the third is electrodeformation, very similar to what I explained earlier, where you measure the deformation and try to back out the electromechanical properties. In capsules, for example, the electrical property of interest is the membrane capacitance, and one would like to estimate it using theoretical models for the deformation. Okay. So with this, I start with the first part, which is a water in water capsule under DC fields. And as I said, DC fields are applied, very strong DC pulses are often applied in electrochemotherapy, for example. And normally, what you see is you apply pulses, strong pulses of 1 millisecond to a few microseconds, and the cell gets sporated, and that's what the typical experiments have been. Okay. Now, these experiments have been mostly on liposomes or vesicles. Okay. So I am going to cheat a bit here, in the sense that I will show experiments with vesicles and liposomes, and I will try to predict them using the elastic capsules. Okay. And in the process, I will try to argue that it's the electrostatics which plays a more important role than the membrane mechanics. Okay. So these are the experiments. What you have here are ITO electrodes, and we do experiments with liposomes. These are SOPC vesicles or liposomes, giant unilamellar vesicles made by electroformation. And then you apply a very strong pulse. We've applied kind of 8 pulses as well, but what I'll discuss today is you just apply 1 pulse of around 1 millisecond. Okay, so 1 millisecond of 1 pulse, and a significant deformation happens when you apply a strong electric field. The electric field is typically 1 kV per centimeter. 1 kV per centimeter is kind of the ballpark field which is used for electroporation, so you're almost in the electroporating regime. And a significant deformation is observed, is expected, which has, at least to the best of my knowledge, been observed only once in the Dimova group, which I will show. And the reason for that is because you are using a pulse width of around 1 millisecond and the deformation happens over 1 millisecond. If you use an inverted microscope, you are typically used to frame speeds of around 10 to 50 frames per second. And so if you want to access 1 millisecond, you have to do a bit of changes in your microscope. What we did was to replace the regular halogen lamp with a 250 watt lamp, and then the imaging is done for very short time because you would otherwise burn your objectives. And these experiments were indeed motivated by similar work in the Dimova group. So what the experiments I show are basically our experiments which give the same results as the Dimova group, but the theory is what I would be interested in. So let me just get it right that the globules here are liposomes, they are not elastic capsules. Okay. And what you see here is this very fast dynamics. You see the dynamics happening over 1 millisecond, and you see significant shape changes in the vesicle. Okay. This is the applied electric field. Okay. And what you see is that these vesicles can form what I call as prolate cylinders, because this is what you would call a prolate shape, this is what you would call as oblate shape if this is the axis of symmetry. And you see prolate deformations if you use glucose. But what is interesting is if you add salt in the outer medium, so if the outer medium is more conducting, you see oblate vesicles. and these vesicles are fairly cylindrical in shape. Okay. Now, yeah, let me just go back to here. So these are the more common experiments in electrodeformation of vesicles, where you get spheroids. Okay, you get prolate spheroids or you get oblate spheroids when you have vesicles in electric field. Okay. However, what you see in strong DC fields are shapes which are not spheroids for sure. They are kind of fairly cylindrical in shape. Okay, and then you switch off the pulse, and then it of course relaxes back to a sphere. Okay, and as I said, this whole imaging is possible only with some improvisation in your microscope. Okay, so the idea, so of course, as I said, the whole idea was to reproduce few of these results from Risk and Dimova, who did kind of similar manipulations. The images are much better. I would like to mention here that these images are using a CMOS camera. In our case, we use a Phantom Milo 10,000 FPS. Okay. Now, so one has to first understand the electrostatics of these membranes, and the difference now from what I did earlier was that if you have a membrane, you have now aqueous phase inside and outside, and in this case there are three important timescales which one has to be aware of. The first is simply the charge relaxation time in the bulk fluid. So it's, suppose you have a few charges in the bulk, the charges get dissipated with the dielectric constant of the medium divided by the conductivity, or the permittivity of the medium by the conductivity. Okay. Now, if you have an interface, on the other hand, there are charges which build at the interface, and these charges build over what is called as the Maxwell-Wagner relaxation time, which is the ratio of the permittivities of the two fluids and the conductivities of the two fluids. So it depends now on whether you have a higher conducting fluid inside or a higher conducting fluid outside. Okay. So for example, if we have a higher conducting fluid inside, you would have in this scenario, for example, a positive charge deposited at the interface, whereas if the outer fluid was more conducting, you would have a negative charge built at the interface. So there is a net charge at the interface, and this charge builds over the Maxwell-Wagner relaxation time. Okay. Now, if you look at aqueous phases, this Maxwell-Wagner relaxation time, even for deionized water, is around 100 microseconds. Now, what happens if you have a membrane? If you have a membrane, it's like the membrane is typically a dielectric, so you have a thin spherical, you can imagine this to be a spherical capacitor. And as you know, a capacitor gets charged over what is called as the charging time of a capacitor, which I call T cap here, and it depends on the capacitance of the membrane. Okay. Now, because you typically, at least in bilayers, you have a 5 nanometer thin insulating layer, the non-dimensional capacitance, for example, turns out to be around 50 to 100, which means that the charging time of the capacitor is at least 100 times that of the Maxwell-Wagner relaxation time. Okay. So for deionized water, if you have 100 microseconds as the Maxwell-Wagner relaxation time, you will have around 5, this should be milliseconds, okay, around 5 milliseconds of the membrane charging time. And this gives us access to frequencies. For example, you can access Maxwell-Wagner relaxation time in deionized water with around tens of kilohertz of frequency. You can have now membrane charging time accessed by around 500 hertz, okay. And this then becomes very accessible to experiments, okay. Now, these are large deformation, and so I would use the boundary element method. We have this boundary element method here. We use the Skylark Law and the Muni-Rivlin law in this part. And the equations are the same as I said earlier for the membrane part, except we need to add a bending term to prevent numerical oscillations in our calculations. And the bending term has a Beltrami operator acting on the curvature and the nonlinear curvature term. Okay. Now, the boundary integral equations now are different because the membrane admits what is called as the transmembrane potential. Okay. So, you have to write a separate equation for the internal phase and the external phase, and these two potentials are not the same, and they are not the same by a difference which is called as the transmembrane potential. The boundary conditions you use here are the electric continuity equation. So, you have the ohmic, so let me just go here. What you essentially have is the ohmic conductivity as well as the displacement current. So, ohmic and displacement current of the internal fluid is the same as ohmic and internal displacement current of the outer fluid, which is the same as the ohmic and displacement current of the membrane. Okay. So, this is the ohmic and displacement current of inner, and this is the membrane displacement current, and this is the membrane ohmic current. Okay. Now, typically the membranes are insulating, and one can assume that the conductance of the membrane is 0, and I would later show that this makes a significant difference in the response of a capsule to electric field. Okay. Sorry, just 5 minutes. Oh, okay. So I think I'll just end with this part then. So we do the boundary integral formalism. I can maybe skip this. We do analytical theory for this, and this is what you get. So at least let me explain this properly. So what you have here is the degree of deformation plotted as a function of time, and this is plotted now for the Muni-Rivlin and Skylark models, and for two different conductivity ratios. Okay. So now if your outer conductivity is more, then you have sigma r is 0.1. If the inner conductivity is high, then you have sigma r is 10. Okay. Now, if the inner conductivity is more, you actually see the membrane deforming into a prolate shape, and then it relaxes back into again a prolate shape. Okay. So it starts with 0, reaches a prolate shape, and then relaxes back to a prolate shape. If the outer conductivity is more, then it starts spherical, ends up in a oblate shape, and then relaxes back to the same prolate shape. Okay. So you find that the end shapes is independent of the conductivity of the medium. Okay. So how do you explain this? Okay. So now if you are at very short times, which is at very high frequencies, you know that the membrane impedance is almost 0. If the membrane impedance is almost 0, you don't have any charging of the membrane. If there is no charging of the membrane, no charging of the interface, there is no free charge anywhere, and so there is no Maxwell stress, because the inner and outer fluids are kind of the same, and if there is no Maxwell stress, you get 0 deformation. So it does not depend on the conductivity. Now, in the intermediate time scale, that is between the Maxwell-Wagner time and the membrane charging time, the membrane starts getting charged, and now if your internal medium is more conducting, you see that there are more positive charges here, so just for reference, this is the positive electrode, this is the negative electrode. You have more positive charges here which get attracted to the negative electrode, and you get a Maxwell stress distribution which looks like this. On the other hand, if your outer medium is more conducting, you get a net negative charge here with the net negative electrode, you get compressive Maxwell stress at the poles. Okay. So you now see that the stress distribution is sensitively dependent upon the conductivity of the inner and outer phase, and it could be tensile at the poles or compressive at the poles. Okay. If you go to very long times, that is very short, very small frequencies, the membrane impedance is significant. If the membrane impedance is significant, the normal electric field has to be 0, because the current has to be 0. And if the normal electric field is 0, one can show that the normal stress now comes only because of the tangential field. Okay, there is some complication with the Maxwell stress. You actually have the Maxwell stress as normal electric field square minus the tangential electric field squared, and because the normal electric field is 0, it's only proportional to the negative of the tangential electric field square. It's kind of not very intuitive. You have tangential field which causes the normal stress, but the tangential stress is 0. Okay. And in this case, what you get now is, because the normal electric field is 0, it doesn't matter what your conductivity is, and independent of the conductivity, you get a Maxwell stress distribution which looks like this, and therefore the deformation now comes to the same value. Okay. Now, if you go to large capillary numbers, and I'll probably end with this, if you go to very high capillary number, this is the sequence of event that happens when your outer medium is more conducting. Okay. So at short times, as I said, when the outer medium is more conducting, just beyond the Maxwell-Wagner relaxation time, you have strong compressive Maxwell stresses at the poles, which try to squish it into an oblate shape. And when it squishes into an oblate shape, you can monitor the azimuthal and the tangential, azimuthal and the meridional tension, and you find that the azimuthal tension is tensile at the poles. And then what happens is, the stresses are so large because your capillary number is large. Okay. And remember that the membrane is simultaneously charging up completely as it deforms. So if the capillary number is large, the strong Maxwell stress at the poles lead to a depression at this point, which forms kind of a biconcave shape. Okay. In the meantime, the membrane is discharging, and we know that for the membrane is completely charging, and we know that when the membrane gets completely charged, you would have a strong compressive stress at the poles. So this is what it's finally heading to. So in the intermediate stage, you have we have kind of compressive stress at the equator, compressive stress at the poles, which leads to this square cylinder shape. And then it relaxes back. When the membrane has got completely charged, we know that the Maxwell stresses are maximum at the equator, they are 0 at the poles, and it then forms a prolate shape. So in the intervening time steps, the computation of these compressive Maxwell stresses which go from poles to equator and the corresponding deformation leads to an intermediate cylindrical shape, which you actually see in experiments. Okay. So I'll stop. You actually see that at the end of this, the azimuthal tensions would have become compressive. Okay. One is interested in transmembrane potential in such highly deforming systems, and one sees that in the intermediate range where you have fairly cylindrical shapes, the transmembrane potential is fairly constant, and this actually brings out possibility of poration of a large region at the poles. Typically it is known that normally only the poles porate because the transmembrane potential is maximum at the poles, but when you have large deformation in the system, you could have poration in a large part of the membrane. So I think I'll stop with this and yeah, I'll take questions.
We have time for a couple of questions. Yeah, Professor Mahesh.
Rochish, very nice talk. So towards the end, you had these measurements of the impedance for varying frequencies, I think.
Yeah.
So the question is that, for impedance spectroscopy that they do for measuring the properties, let's say of RBCs and so on, in fact, they find a variation of the impedance as a function of the frequency.
Yeah.
So have you tried so are there similar experiments that are done for vesicles which you can compare?
No. So here, the membrane impedance is governed by the membrane capacitance, which I assume constant in the system. It's kind of is 50 in this, it's non-dimensional number. It's basically the membrane dielectric permittivity divided by the thickness of the membrane.
Right.
So you can get some microfarad per meter square.
Right.
And that I've kept constant. In impedance spectroscopy, I think you have, so now the impedance changes only because of frequency.
That is true.
But the membrane property is remaining constant.
So there, my understanding is that they measure the overall impedance between the two plates.
Yeah.
So in one case at low frequencies, I think the current just goes around the vesicle.
Yes.
And at higher frequencies, it starts going through because it starts conducting.
Right.
So my question was, are there similar experiments for vesicles which you can compare predictions against?
No, not really. Okay. But I would expect non-trivial things only if there's poration. Then you have membrane conductance GM, which I had ignored. And then you would have a loss and a storage part to this. And that can then change the membrane impedance significantly.
Yeah. So I guess in experiments at about 4% increase in the membrane area, you get poration, and typically you see a flux of water across the membrane. So in your modeling, how is the water?
I have not. So there are that's the next thing I want to do, where I could now put the membrane conductance as a function of the transmembrane potential. It's something I have on mind, because we know that around transmembrane potential of a volt, the membrane porates. And now that I have a distribution of transmembrane potential, I can actually put some membrane conductance proportional to the transmembrane potential and then redo that. But I would just, if you allow Devang, just one thing. This is for AC fields which I couldn't show results. There are significant results here. But this is the difference you see. So this is deformation versus frequency for inner medium more conducting or outer medium more conducting. You get a very complex phase diagrams. This is kind of oblate oscillations of a vesicle. But if you include membrane conductance, you see significant change in the deformation pattern. This is again for a fixed membrane conductance. I have put a fixed membrane conductance. It's kind of an artificial thing. But it shorts the membrane, and once you short the membrane, you can't charge the membrane. If you don't charge the membrane, the deformation completely changes. That's why.
Thank you.
Any other questions? Okay, then let's thank the speaker one more time.